Okay, let's get straight into it. Relative atomic mass. A pretty fancy name for something that you're basically already familiar with. And essentially it's just the idea that the actual mass of an atom is just too small to measure. So if we wanted to try and weigh the mass of an atom, so use something to measure the mass of an atom, it's just far too small. We can't put a single atom on a balance and try to determine its mass. So atoms were given a mass that was relative to the other atoms. So it's not an actual value, it's not like kilograms or grams, it's just relative to the other ones. So for instance, the relative atomic mass of hydrogen is 1. And that makes sense. Hydrogen is, on the periodic table, we know it has a mass of 1. The relative atomic mass of carbon is 12. So carbon and generally speaking, or on most periodic tables, it would have a mass of 12. Now in real life, the relative atomic mass, it is all relative, they're all relative to each other. It's actually based on carbon. So it's not actually based on hydrogen. Hydrogen is 1/12 that of carbon, whereas other ones are larger than carbon, so it's all relative to carbon. So why is this important? Well, it's got to do with isotopes. And before we look at what this word isotopes actually means, let's start by trying to answer this question. Why does carbon actually have an atomic mass of 12.017? So if you look on a lot of periodic tables, it's been rounded to 12, but on a lot of them it still has the actual atomic mass, which is 12.017. Well, you guys know the atomic number means that it's here 6, means that it's got 6 protons, and the mass number is the total number of protons and neutrons. So you might think that carbon has 6.0107 neutrons. But do you really think that we can get 0.107 of a neutron? Do you really think there's this tiny piece of a neutron inside there? No, there's something else is happening here, and it's basically this. So there are actually slightly different versions of carbon that have a slightly different number of neutrons. So here on the left in this picture is carbon 12. It has 6 protons and 6 neutrons, so a mass of 12. This is carbon 14. It has a total number of 14 protons and neutrons. So in this case it's got 6 protons and 8 neutrons. So the difference between these is simply that one of them has a few extra neutrons. So 98.9% of carbon atoms have 6 neutrons. However, a few have 7, and some even have 8. And so the one that has 8 is actually this one here, known as carbon 14, because it has a mass of 14. Right? And that one's actually sometimes used in carbon dating. You may have heard of that. So this means that the relative atomic mass of carbon, if we had a lump of carbon, its actual relative atomic mass is actually slightly over 12, because normal carbon, or one of the forms of carbon, has 12, a mass of 12, 6 protons and 6 neutrons. However, there's a few versions that tend to have slightly more neutrons, so on average it'll be just over. Just like if I asked what the average age in the class is, if most people in the class were 13, but 1 or 2 people were 14, well then the age would be just over 13. So a few versions of carbon, a few atoms that have an extra neutron, bring their average just over 12. So this is what we call isotopes. Isotopes, and this is something you actually need to know for your test, so the definition of isotope is just different versions of an atom that have a different number of neutrons. So it's still carbon, it still smells like, tastes like, feels like carbon, it just has a slightly different number of neutrons, which changes its mass slightly. So isotopes still generally have the same chemical properties. They react with the same elements and all those sorts of things, because the number of valence electrons hasn't changed. And in the same way, they're still the same type of atom. They're still the same element, because they've got the same number of protons. But they've got a slightly different number of neutrons. So isotopes are different versions of an atom that differ in the number of neutrons that they have. So if we look at chlorine, chlorine has an atomic number of approximately 35.5. It's actually more like 35.45, but let's just say 35.5. In reality, about approximately 3/4 of chlorine atoms have an atomic mass of 35. So you can see here in my little scale picture here, 3 of them have a 35. So 3/4 of a cloud of chlorine gas, of those atoms would have 35, an atomic mass of 35. And roughly 1/4 have an atomic mass of 37, slightly heavier. So this gives chlorine a relative atomic mass of 35.5. So these are two common isotopes, or the two most common isotopes of chlorine. There are still tiny amounts of, you might even get chlorine with an atomic mass of 38, or that has even more or less neutrons. But most chlorine atoms either have 35 or 37. So this one's quite interesting because it fits, it sort of falls almost smack bang in the middle, 35.5. So sometimes even when it's rounded, it's left at 35.5. It doesn't mean there's half a neutron in there. It means some of them have less neutrons and some of them have a couple more. And that's why the average comes out at 35.5. So the two most common isotopes of chlorine are chlorine 35 and chlorine 37, and that refers to their atomic masses. So even though 35 is the most common, it's still an isotope. So isotope isn't just the other versions, it's all possible versions of an atom. So when you see the word isotope, just think of it as versions. It's isotopes of an atom are the different versions or the different numbers of neutrons that element can have. Alright, relative formula mass. To find out the relative formula mass of a compound, you just add together the relative atomic mass, the RAM, values for all the atoms in its formula. So let's have a look at this. So, for instance, hydrogen here, let me get out my pencil. Hydrogen here, hydrogen has a mass. Hydrogen, sorry, trying to talk and write at the same time. Hydrogen has an atomic mass of basically 1, or at least its most common isotope does. Oxygen, so we'll just round up to the nearest number, because that'll be most likely be the most common isotope, the most common version. Oxygen has an atomic mass of 16. So in this case, the relative formula mass for H2O, 2 hydrogens and an oxygen, means the total, so hydrogen times 2, means our relative formula mass is 18. So the relative formula mass of H2O is 18. So let's look at this one here, C6H12O6. You're not expected to know that, but that is actually glucose or sugar. So for sugar, let's go through that. Carbon has an atomic mass of, we're going to go with 12. Alright, because 12 is the most common isotope, so we'll just round to 12. And we've got 6 of those. Hydrogen has an atomic mass of 1, and we've got 12 of those. Oxygen has an atomic mass of 16, and we have 6 of those. And now we really put my maths to the test. So 6 times 12, so that's 72. 1 times 12, I can do that one, 12. And 16 times 6, I believe that is 96. Cool, so we add all that up. 72 and 12 is 84. 84 and 6 makes 90 plus 90 is 180. Okay, my apologies if my maths is incorrect there. But guys, I think you get the point. I'm just trying to show you the process. I don't have a calculator in front of me. I'm doing that in my head. So if I made a mistake in my maths, my bad. But you'll just have to forgive me. Okay, so guys, for the relative formula mass, It is just a matter of taking the atomic mass of the element and timesing it by how many of that atom or that element are in the compound, and then adding it all together. Cool, let's clear that and we can carry on. Alright, so the last little bit that I wanted to talk about is the law of the conservation of mass. So the total mass of the reactants is always equal to the total mass of the products formed. So in a chemical reaction, the mass is conserved. It doesn't change. The total mass of what we start with, the total mass of the reactants, equals the total mass of the products, what we finish with. So looking here, if I've got carbon plus oxygen makes carbon dioxide, well, carbon has an atomic mass of 12, oxygen an atomic mass of 16, but we've got 2 of them there, so 2 times 16, and carbon dioxide is 12 plus 2 times 16. If we add that all together, so that's 32 plus 12 is 44. If you add them all together on both sides, you've got 44 on both sides. And you can do that in real life. You can use actual physical masses of that too. So if I take 12 grams of carbon and react it with 32 grams of oxygen, I'll get 44 grams of carbon dioxide. And you notice here on this side, in terms of reactants, we've got 44 grams of reactants, and here 44 grams of products. So that the weight, or rather the mass of the reactants is always equal to the mass of the products. And that's really it, basically, and that kind of makes common sense. But it was fundamental to the early discovery of some of the elements and how chemistry worked was that one of the earliest chemists figured out that the mass is conserved, and then they were able to look at in what ratios certain things combined to form certain products. And by working out the ratios, that's how they started to realize they could actually write these formula for those things and look at how they actually combine together. And by looking at how they combine together, they started to figure out some of the structure of those elements or those atoms and their mass. So this was actually crucial to really the birth of chemistry and figuring out some of that fundamental stuff, was the discovery that the products, the total mass of the products was always the same as the total mass of the reactants. Cool, I hope that helped, and I think that's the last one, so good luck with your test.